So good morning, everybody. Welcome. This is the Machine Learning and Survey Research Workshop presented by PDHP. Hopefully this is the place that you intended to be this morning. If you are here, then you're in the right place. So before we get started, I just want to take a couple minutes and kind of talk about PDHP real quick and just introduce ourselves and what we do. My name is Paul Schultz. I'm the consulting statistician and data scientist, for PDHP. And basically, we're a center inside the Population Studies Center that's charged with sort of stimulating and enhancing population research here at the center and also across campus. So that's the idea. Basically, we try to raise the bar for all our population researchers, and we have a particular focus on early career scientists and those that are tracking to submit funding and receive funding from the NICHD's Population Dynamics branch. So I want to talk a little bit about the resources that we offer. Obviously, you know about the workshops program. That's a free and open to the public thing that we offer here at the center. I'll talk a little bit about our November workshop in a little bit here. We also offer a mentorship program for our affiliated faculty. We offer, just real briefly, sort of administrative resources. And then within the scientific and technical core that I myself work on, we handle sort of the technical and computing aspects of research. So for our wing, we offer a consulting service for our faculty affiliates where we can talk about statistical modeling, statistical methods, data management, really any kind of computing or technical aspect of your research. We're happy to help that, and that's free to our faculty affiliates. We also offer a small grants program to sort of just to help fund pilot projects, computing needs that you might have, pay for software, that kind of thing. We have an open call right now, I believe, until November 1st, if I'm correct. So if you can think, feel free to go on our website. Obviously, all this information is there. If you have a sort of, a small grant type application that you think you might be able to fund through us, feel free to go on our website and look that up. Again, we're open till November. And then we also offer paid time, again, for our faculty affiliates. If you think that you have a need that goes above and beyond what we can accomplish in a few consulting hours, then you can actually, propose to get a fraction of my time and also Chen's time, who's here in the front row. We're both analysts that work on the program, and our time is basically up for hire for projects that need the help. You know about the workshop program. Like I said, you're here. November 12th is going to be our next workshop, and it's going to be sort of our second part of our survey weights series. We did the first part last month with Brady West here in the front row. I believe November 12th is 2 weeks from Tuesday. So we'll be getting the announcement officially up probably early next week, and you'll see that hit your inboxes. And we hope to see you there. He'll be talking more about sort of the production side of weights, basically what are we trying to accomplish with weights, best practices for creating and releasing weights. Anything else I'm missing, Brady? I think that's it. So yeah, that's going to be November 12th. Hope to see you there. And then the last thing I want to mention with PDHP is we also do a coder space every Tuesday morning from 10 to 11:30. It's really just sort of a networking type opportunity, and also it's sort of like office hours. So Chen and I are there on hand. Feel free to bring any sort of geek-related, technical-related research or problems that you might be having. We're happy to answer questions. Or really just, it's really just there so you can meet each other, and it doesn't necessarily have to be a question-answer format. We're really just kind of there in the room, sort of coding together, and it's meant to be more of like a community-building thing. So again, that's Tuesdays 10 to 11:30. It's actually right across the hall here in 1430. So if you feel free, we welcome you to come to that. I believe that's it. So I already mentioned the November workshop. I think we're all set. So are there any questions about the center before we get going? Again, everything's on our website. If you feel that you or a faculty member that you're affiliated with would be interested in applying, the details are all on our website. Feel free to either talk to me today here, send me an email later, or just get the details right from the website. So with that, I will go ahead and introduce our speaker for this morning. Here's our speaker here. Adam Eck is an assistant professor of computer science and leads the social intelligence lab at Oberlin College. He received his PhD in computer science from the University of Nebraska at Lincoln, where he was also a postdoc in the survey research and methodology program. Adam's research interests include interdisciplinary applications of artificial intelligence and machine learning to solve real-world problems, such as data science and machine learning for improving data collection and analysis in the computational social sciences, e.g. survey informatics, as well as decision-making for intelligent agents in complex environments. So you'll have the floor until 1 p.m. Thanks again for coming, and have a great day.
Cool. And thanks everybody for being here. We've got a great crowd today. This is really exciting. Thanks to all of our participants that are connected remotely as well. So yeah, I guess I'll go ahead and just get started. So this is a workshop on machine learning for social science in general, but themed a little bit for survey research. So acknowledgements, this is based on a short course I gave at APOR this year, hence the survey theme for this, but I've extended it for what we're going to do today. And I've also based the slides on a whole bunch of different sources. Some of this is stuff that I actually use in my machine learning class that I'm teaching this semester again, and also some conference talks to bring in some real-world examples and stuff. Okay, so I'm hoping that this workshop will be very interactive. Feel free to stop me with questions at any time. Hopefully there's a way to make that work for our remote participants as well. But I also want us to sort of think about some concepts and then talk with your neighbor about things too along the way. So let's just start out with everybody think for a minute or two about sort of what do you think of when you hear the term machine learning? We're all probably coming at this with very different backgrounds, different experience, different sort of knowledge of the field. So let's just think to ourselves for a little bit about what we think machine learning is, and then we'll talk with a neighbor in a bit too. We'll start with that. Okay, let's go ahead and come back together as a group. So who wants to share some things that their table was talking about? What are some things we think of when we hear machine learning? Yeah.
Finding a function from very noisy, like the true function from very noisy data.
Awesome. Other thoughts people had? Yeah.
Like the main method to like grant neural network and a forest.
Awesome. If I can spell. What are some other things we talked about? Yeah.
Coding textual data for open responses from surveys.
Ah, awesome. We'll definitely come back to that one. Other thoughts people had? Okay, so it sounds like looking at these three, we've got sort of a general idea of what machine learning might be trying to accomplish, some different techniques we can use to serve that purpose, and then an application that we could work this in. So those are really common things to talk about, sort of what machine learning is, how we use it, and then what the applications are. And that's actually going to be the outline of today's talk and the workshop today, so I kind of like that it came out that way. Great. Okay, the objectives for this workshop, let me go back to presentation mode. My big goal today is that hopefully we can walk through and explore why and when machine learning might be a useful technique for us to use. So think about this not just as a set of statistical methods or other things, but really looking at it from the problem-solving perspective. What kinds of problems exist that we might want to use machine learning for? And along the way, we'll introduce some key terms and ideas so we get an idea of sort of what the field is and what it's talking about. And then we'll also highlight some advantages and disadvantages of different techniques. So not only knowing when to use machine learning, but when to use different things inside of it to solve our problem. We'll illustrate that with various actual real-world applications, and then we'll do some demonstration with code. So hopefully everyone found on the webpage there's an R Markdown file and also a Python Jupyter notebook, along with HTML pages that have that code inside of it. We'll walk through those examples as we go through today. So if you have experience with R already, awesome. If you're a Python person, awesome. If you want to see sort of what happens in the other programming language, we'll look at both of those today. Okay, so agenda-wise, we're going to spend the first part just talking about what is machine learning, sort of unpacking this idea that we were just talking about in groups. We'll talk about it as a problem-solving paradigm and then compare different kinds of machine learning. Usually when we talk about machine learning, especially as an analysis technique, we think about one particular type, which is supervised learning, but we'll also talk about some other ways that it might be useful too. After that, we'll go through a very detailed example of how machine learning works. We'll go through the entire pipeline. So starting with having access to a data set, to training some machine learning models, to evaluating how good they are in the end. And then we'll look at several popular methods. So some of the ones that were mentioned a minute ago, we'll look at random forests and neural networks, and then also decision trees as well. And along the way, we'll look at different applications. So when we do our big workflow here, we'll look at a particular application of predicting who's going to actually respond to a survey or an interview request. And then time permitting, we'll look at some other ones like text labeling. So the open-ended coding response. So taking this text data and assigning codes to it. We'll talk about how that differs from other applications of machine learning. We'll look at some image analysis. I've done some research on trying to take aerial images to find locations of interest to build sampling frames. So a very different kind of data, and we'll look at sort of how machine learning works in that sort of application as well. But this will be the general flow today. Any questions about anything before we get started? Okay, great. So we'll start out with just what is machine learning? So if I had to give a definition for it, and there's lots of different ways of looking at it, but the definition I like most is if a computer learns if it improves its performance on a task over time based on experience. So several key ideas here. We've got a task, we've got improving performance, it doesn't happen instantaneous, it happens over time, and it needs experience. So looking at that, there's always three main things we look at when we decide, is machine learning good for a problem? So the first thing is there a particular task we want the computer to be able to accomplish for us? So in our survey non-response or our survey response prediction, the task here is having the computer tell us in advance who's going to respond or not, or what are their likelihoods of response. The computer's not going to be immediately good at that task, but it's going to start somewhere and get better over time. So we need some way of being able to measure how good it's doing so it knows how to learn. So it's not enough just to give the computer a lot of data to work on a task. It has to know, sort of be able to evaluate itself, am I doing well right now or not? So we might look at things like accuracy of predictions and some other measures there. Then ultimately, what drives all this learning is experience that we provide to the computer. So this is the data we have collected that it looks at several different times to find patterns and functions and all the things I heard some groups talking about, but finding some way from the experience, some pattern that tells it how to do the task, and it improves its performance over time. So anytime we want to try to use machine learning, we want to be able to identify these three things in our particular application. Okay. So let's talk in small groups again real fast. So thinking about just the task side of this. If you could get a computer to do anything at all for you in the world, what kinds of tasks would you want it to learn how to do? And then maybe think about that in the perspective of your everyday life, but then also in your work too. Let's just think if we can generate a bunch of different tasks that we might ask machine learning to solve for us. Go ahead and think for a minute, and then we'll talk about it. Okay, I'm hearing lots of great conversation. Let's go ahead and come back together, though. So what are some tasks that people talked about? Maybe just in your daily lives first, and then we'll come to the work example afterwards. So what are some things we wish computers could do for us to help us in our lives? Yeah.
Tell me what I should wear based on like what I have, what clothing is clean, what the weather is.
Sure.
That kind of stuff.
Great example. Yeah.
What stocks to invest in?
What stocks to invest in? We might never have to work again, and solves the second question. Other things people talked about. Yeah. Sure. So it uses some machine learning already, but it could always be better. Maybe being smarter about when to even try to autocorrect and stuff. Awesome. Another one.
Mine was related to that.
Okay. Guess we don't like autocorrect. I don't either. Oh, sure. Any other examples?
Cars drive for us.
Autonomous cars. Yes. On the one hand, it would be kind of nice to not have to drive and be able to do other stuff while we're in a car. On the other hand, I'm not a little afraid of what the world will be like when robots take over in terms of driving and stuff. But yes, great example. Any others?
Prediction the result of the game and to bet on the game.
Sure. Sports prediction. So we don't have to be in Back to the Future and go find a book that tells us who all the winners were. We could let the computer do that for us. And again, like stock investment, we could make a bunch of money off of this. Okay, these are great examples. So what about things that we wish computers could do for us in our work lives? What are some tasks at work we'd like them to do? Yeah.
We talked about building networks, so in either like social science or psychology, there's different ways to find like groups or
Sure. Awesome. Yeah.
I think maybe for like a quick review, like a topic I'm interested in. Take a quick review for me.
That would be a fantastic one. So we can give it a topic, it goes and finds papers for us, maybe even summarizes them so we don't need to read them in the first place. That would be great.
From the chat, we have speech recognition and record linkage.
Awesome. A lot of speech recognition stuff is done through machine learning. How many people use Siri or a Alexa or Google Home or the other ones? Okay, a couple people. I've asked this question for like 5 to 10 years, and the percentage of people that raise their hands doesn't tend to change very much. It's kind of interesting. But all of that's based off of machine learning too. So it trains it has lots of data of different people talking, and it uses that to predict what people are saying and that kind of thing. And some of those models are actually downloadable so that you can find someone else's model that they've built and add that to whatever you're trying to do. So we don't have to reinvent the wheel on those, because speech recognition in general is a really hard one to do. Other tasks. Yeah.
Taking your email and pulling out a calendar appointments or actionable to-do.
Even prioritizing which emails you should reply to in which order. Amazing. Definitely wish I had that capability. Any others? These are all really good. Okay. So, a few that I had jotted down in here. It's not fair for me to ask everyone what they think without giving my own. So if I could get a computer to automate any task in my general life, I'd love something that could write choose-your-own-adventure stories for me. So I have a 4-year-old daughter. One of our favorite things to do together is to read stories every night. The challenge with a 4-year-old is they like the same stories over and over and over and over. And so by the end of the week, it'd be nice if it was a slightly different story. And so it'd be cool if a computer could actually generate those things for us. So not only coming up with new stories, but how many people read choose-your-own-adventure stories as a kid? Okay. Some of the room. The idea is that you flip to different pages based on choices you make inside of it. So it gives you a setting, and there's different plot points, so you can say, I would want to do this, and you would go to one page. So here we could actually have adaptive stories on the fly. So not only comes up with a new one, but based on your choices as you go along, you can choose these. Netflix had some shows that are trying to work in this kind of space now, too. So that'd be the task. The performance, how we'd measure how well it's doing, would be user satisfaction. So if the user is happy with the stories, then we want to create ones that are similar to that again in the future. If they don't like something, then don't try that again. Experience here, it could learn from past stories, so reading through things that other people have written to get a general idea of what to do. But then it can also adapt based on user choices. So if one user tends to like the same type of story, then it's more likely to generate that one again in the future, and that kind of thing. If I could use machine learning for any task in work, I would love to have an automated assistant. So something that I could use to help me with my research, to help with email answering and other things that we talked about too, handling different day-to-day tasks through my job. Here the performance might be how helpful it is. So it's one thing to write something that can prioritize your emails or reply for you. It's another that can do it well. And so we'd have to be able to measure those kinds of things. The experience here would be outcomes from interacting with people. The tasks that we're going to look at later on in the talk. So one, again, was this idea of non-response prediction, deciding in advance who's likely to respond to a survey or interview or not. Our performance would be the accuracy of those predictions. So how many did it get right when we actually use this in the real world, or when we make predictions on past data. And the experience would be how people have responded to previous surveys. So looking at sort of the entire sampling frame, and then what their characteristics were, and then who actually responded and who didn't. In terms of building that sample frame in the first place, this was the idea of using aerial images to find locations that we might want to survey. So one example that we were looking at was trying to find all the windmills in a state. That way we could understand more about clean energy production and those kinds of things. So here, if that's our task, our performance would be how well does it actually cover the target population? Does it have too many false positives where it's identifying things that aren't part of our population? And then does it actually find the real examples in there as well? So we give it plenty of examples of the target population to learn from. So for us, that's a bunch of aerial images where we say this is a windmill or this is not a windmill, but you could use this for any other kind of sampling frame too. Finally, the idea of text code response, coding text responses and things. There would be the matching between automated and manual codes. So we would have, there still has to be some person that goes and assigns codes, at least in the beginning of this. And then we would see what gets predicted by the machine learning model and see if it's the same code, yes or no. And we'd give it those manually coded responses as our examples for it to learn. Okay, so we talked about lots of great tasks. We see that there's different performance measures that we might use on different tasks and different experiences as well. Any questions or comments about this way of viewing machine learning as trying to accomplish a task, improving performance, learning from experience? Okay. So I kind of want to present this now as a problem-solving paradigm. So where machine learning is really interesting to me is sort of the opportunities it's going to open up in the future, especially for people interacting with software. So how many people have done at least a little programming before? R, Stata, Python. Okay, most of the group. Awesome. So the way we usually, the cool thing about computer science to me is that it's more about how do we solve problems as opposed to what code we physically write. So for the intro class, the way I frame it, which is one of my favorite classes to teach, is it's just about problem solving. How do we take something in the real world, something we want to be able to do, and how do we get a computer to do that for us? Programming is the way we give it instructions, but the real step is how do we take a problem, come up with a solution, and then actually build that solution. So the way we usually write software or get computers to do things for us, we start out by designing an algorithm. We think about what our problem is, and we come up with the right set of steps to be able to solve that. How many people in the room enjoy baking or cooking? A good number. Baking's one of my favorite hobbies. Recipes are algorithms. So algorithms are all over in the world. They're not just the things that we do in software. They're anytime we have a sequence of steps that help us solve something. So coming up with the right list of ingredients, mixing them in the right way, baking them for a certain amount of time, all part of an algorithm. And so a lot of the work to actually getting computers to solve things for us is in this step, coming up with the right algorithm, the set of steps it should take. After we've got our algorithm, then we translate it into a way that the computer understands. So this is where we use the programming languages. We take our concepts that we've been thinking about and maybe can describe to a neighbor in our favorite language, English or whatever, and then we want to be able to turn that into a computer language. We're going to actually write our code that's going to then follow the algorithm and solve the problem. After we've got our problem, our program, we run it, it performs a task for us, we're done. So this is the standard way that we've been doing things since the 1940s. Machine learning kind of turns that on its head and gives us a completely different way of accomplishing the exact same thing. So rather than having a human sit and think for a while about what the algorithm should be to solve a problem, we really just need to collect examples of something accomplishing the task for us. So in our text coding example, we just need examples of codes people have given. For non-response prediction, we just need to know in the past who's responded and who hasn't. Examples of what's the right answer for this particular task. We then feed those examples into a program, some sort of machine learning algorithm. So this could be the neural networks, this could be random forests, and the other things that we mentioned earlier. So we're not designing these algorithms. Someone else has one that has a way of processing through lots of data to find patterns in order to know how to accomplish a task. And at the end of this, we have what's kind of like a program. We have a model, at least, that can transform an input into an output, and then we can run that instead. So the cool thing about this machine learning paradigm is this is much more natural of how we've been solving problems for a really long time. Whenever we're learning about a new field or trying to accomplish something new, we go and see what's out there. So the lit review example was mentioned. Most of us probably do lit reviews when we try to start something new so that we know what's already been accomplished. This is kind of like that. We just collect examples of how do we do this thing. When we're learning math, we work through lots and lots of examples on a board ahead of time. And so this is another way of solving a problem as opposed to this. We don't have to know programming languages. We don't have to be able to come up with our own algorithm to solve something. We let the computer do all that work for us. So as long as we can collect enough examples about the thing we want to be able to do, and we have a way of telling it how good it's doing as it's trying to work through those examples, machine learning can do a lot of the work that we would normally do in writing software. And so over the next 10 to 20 years, we're going to see a lot more of user-generated software and programs and things that come from this paradigm as opposed to this one. So anytime you need to be able to do something new, we can have something where you collect data, and then it will figure out on its own what to do, as opposed to having to know how to write programs and stuff. The main idea here is that it's just a different way of looking at solving a problem. If we want to talk about how machine learning works, any questions about sort of the paradigms first? So to be able to talk about how machine learning works, it's helpful to know sort of what the terminology of things are. So a couple key terms that we're going to use here, and I'll relate these to other things you've probably heard before. So we talk a lot about features and attributes in machine learning. And all that means is those are our independent variables. Those are the things we measure about the world that we have information about. So if you're working with a spreadsheet, these are your columns. These are covariates and statistics. Lots of names for the exact same thing. But this is what we're measuring about the world in our experience. An instance is going to be one particular thing in the world that we have all these values for. So if we're trying to assign a code to a text response, that text response is going to be our instance. If we're trying to predict whether someone's going to respond to a survey, then the person is an instance. So this is just a collection of values, one for every single attribute. So looking at this from a spreadsheet perspective, this is a row. We might also call these observations, data points, etc. Again, lots of names for the same idea. When we want to be able to predict or label something, we call that the label. So if I'm trying to assign a code to a text response, that code is the label that we're assigning to an instance. These are our dependent variables or the outcomes we're interested in. And a prediction of whether someone's going to respond to a survey or not. And lastly, the types of things the label could be, those are our classes. So respondent versus non-respondent would be two possible classes, and the label would be one of those. If we're coding a text response, we might have lots of different coding schemes. So maybe we're interested in the topic that they were talking about, so each particular topic would be a different class, and picking one of them for the instance would be a label. Anytime that our classes are categorical, meaning we have a specific number of them that are all different from each other, then those, we call that a classification problem in machine learning. And anytime it's a number we want to predict, then it's going to be a regression problem. Similar language to statistics. We have slightly different methods depending on which one of those things we're trying to do. Okay. So just an example data set that we'll be playing with later. So here's a whole bunch of respondents to a survey. Our labels are whether or not they actually responded or not. Our attributes, we have things like how old they were, their gender, whether they have a cell phone or a landline, their education level, etc. Each one of these things is a separate attribute, and we've got a two-class problem. Question?
Question from the chat. What's the origin of the use of the word label? It seems to be a terribly chosen word.
It is not the best. It has some weird social connotations to it for sure. I don't know the exact history, but I think a lot of it just comes down to it's not always a prediction we're trying to make. We're just trying to assign something to an instance. So I agree that it's kind of a charged language thing that's not the best, but it's kind of nomenclature. So good question. Okay. Any other questions as we go along? Okay. So this is what a data set would look like then. It's just a collection of instances, usually having a bunch of attributes and some labels. Okay. So I mentioned before that there are different kinds of machine learning problems. So different tasks mean we're doing different kinds of learning. And it's important to know for the task we want to accomplish which type of learning we're looking at, because that'll determine what kinds of methods we want to use. So we've mentioned random forests and neural nets and those kinds of things already. Those are all just under the category of supervised learning. We've also got unsupervised and reinforcement as well. So we'll talk more about each one of these in detail, but the big difference is anytime we're trying to predict something for an instance or identify a category or something like that, that's going to be supervised learning. And that's what we usually think of when we talk about machine learning. It's definitely the most prevalent type. Anytime we just want to find relationships in a data set, so which instances are most similar to each other. I think there was a talk about finding different groups of people inside of networks and stuff. That tends to be more of an unsupervised learning problem. Reinforcement learning is what happens when we want the computer to learn how to do a task as it interacts in the world. So actually having a robot go out and do something tends to be a reinforcement learning thing, where it tries something, sees if that worked or not, and then adapts its behavior on the fly. There's lots of other ways we can use reinforcement learning. Okay. Difference here, with these two, we have some sort of data set that we have available ahead of time. With reinforcement learning, we start from nothing. Okay. So let's look at each one of these types in more detail. So supervised learning, the types of tasks we're trying to do here is how to assign something to an instance. So being able to predict about it. So like weather forecasting, deciding what the weather is going to be like today would be a prediction problem. Or trying to diagnose what might be wrong with somebody based on their medical symptoms would be an identification problem. Or topic modeling that we talked about before. Taking a piece of text and understanding what it's talking about would be fitting it into different categories. All of these are the kinds of tasks we do under supervised learning. Our performances here are going to be how well are we actually assigning those categories. I'll try to use categories instead of labels from here on out, based on the question. So one of the main ones we look at is accuracy. So of all the instances, how many did I assign the right category to, or the right value? There's also recall if we want to look at, we'll talk more about these in detail later, but we can also try to figure out for each particular category, how well are we doing. So in medical diagnosis, if we have a rare disease, we can get super high accuracy by just saying that nobody has the disease. Because that's true in general. Most people don't. Well, that's really bad because we want to be able to actually figure out what's wrong with people so we can help them. And so we want to look at the accuracy on just the sick people as opposed to the accuracy overall. So we can look at different types of performance measures here. We call that a class imbalance problem when you have way more of one category than another one. We'll come back to that a little bit later too. In these tasks, our experience always comes down to we have a whole bunch of instances that we know the correct category to. And how we get that can differ. So this is usually somebody by hand is going through a data set and assigning the different categories for us. That might be employees that work with us. How many people have recently used CAPTCHA and try to like prove they're not a robot online? So you get a bunch of pictures and say, where's the car, or where's the signpost, and that kind of thing. Okay, so what's actually happening there is it's not just proving that you're not a robot, but you're actually making robots smarter at the same time. So what's happening is those are all images, those are instances of data, and we're assigning a category. Which ones of these have a car in them and which ones don't? And then that data is then fed into an autonomous car application that's actually learning to identify people and other cars and signposts and other things it needs to know to be able to drive. Does anybody remember the CAPTCHAs where you had to say like what a piece of text was? So that was the same general idea. So that was all for optical character recognition. So we always got presented with two images. One of them, the first one, they knew what the correct word was. So that was deciding, are you providing useful information or not? And the second one was always a word that they didn't know, a picture they didn't know the word inside of. And the point of this was to be able to build digital libraries where we scan in a bunch of books and then they could understand the text that was inside of those to make it more accessible to different people. So there've always been sort of some other purpose behind these proving that you're a person type. Another example of this is Amazon Mechanical Turk. How many people have at least heard of Mechanical Turk before? How many people have used it before? A few people. So a lot of our data sets for supervised learning can also come through there. So we give workers a whole bunch of different instances and ask them to figure out what the right categories are for them. And then we use that as our training data to do the supervised learning stuff. Question?
Question from the chat. Excuse me. What's the difference between experience and performance? For instance, how do we measure accuracy within the instances? Known labels. Oh, sorry. Accuracy without the instances with known labels.
Okay, so that's a great question. And we'll come to this a little bit later when we talk about how to take our data set and use it for different purposes. But the audience member is definitely right that we can't measure performance without experience. So we're going to set aside some of the experience we have that we don't learn from, and we're going to feed that in and calculate our accuracies and other things on that. So we'll save a few of our users or a few of our text pieces and calculate the accuracy on those. So we're feeding some experience into the performance, and be able to evaluate ourselves means we can't learn from it. And we'll talk about why that is later. But the general idea is we don't want the machine learning to just memorize things. Computers are amazing at memorizing information. But if we want to generalize to things we haven't seen, then we can't learn on the stuff we're measuring performance with. Great question. Okay. But this is the general setting for supervised learning. Tasks, we want to assign something to an instance. Performance, how well is it doing? What's our accuracy and other things? Experiences, a bunch of data we already have. So an illustrative example. So in addition to my 4-year-old daughter, I also have a son who turns 2 months tomorrow. And so the idea of trying to baby-proof my house again is coming up and kind of terrifying. But when people are learning, one of the first ways that we do supervised learning is deciding what's safe for us. And as parents, we can help guide our children in this way. So if we think about all the objects laying around in a house, they have different attributes. Maybe what shape they're in, what material they're made of, how big they are, whether they have edges, and whether they have screens. Sort of a more recent thing, but happens more often. And the idea is, can we identify which ones of these are safe or unsafe? So if we look at like a block is a safe toy for kids. The teddy bear is great. Laptops are scary. They can fall, they can break, they can hurt people. Blankies are great. And cell phones, at least when they're super young, not so great either. So if we wanted to learn from this, we can actually build all of our instances. So we've got our attributes, are the things we mentioned before. The shape, what it's made of, its size, edges and screens. And then the category we assign to it is in here as well. So some of these are safe and some of these are unsafe. And so supervised learning is going to take these and look through it a whole bunch of times, figure out if it can find some pattern that leads to safe versus unsafe. We'll hold out a little bit of this to measure how well we're doing, but this is what the experience would look like. Okay. Okay. So let's go ahead and talk in groups again for a second. What kinds of tasks that we talked about before or new ones that you're coming up with would be supervised learning problems? So again, could be something we talked about in groups before or something new now. But we'll start to separate what we've been talking about into the different categories of machine learning. So go ahead and talk with a neighbor, and then we'll come back together. Okay, sounds like most conversations kind of winding down. So let's go ahead and come back together. So what are some tasks people have talked about that have supervised learning? Even got some of the old tasks up here too. Yeah. Sure. Definitely. We've got 2 particular categories we want to understand. Awesome. Other thoughts?
I guess if I had text from like congressional bills, I'd want to be able to put them on a spectrum from, left to right.
Say that again real fast.
If I had text from congressional bills, I'd want to put them on a spectrum from left to right.
Okay. Oh, we'll just say text in general. Awesome. That's not even spelled right. Fantastic.
Sentiment analysis for any sort of like human-coded, prior collected text data.
Yeah. So anytime we want to know the emotions inside that people are expressing when they're writing is a great one. Other thoughts? I like that these are text themed. This is good. Yeah.
Exploring model fit and interactions.
Okay. So in what way?
Trying to find from a large group of data decide which ones to put in the model and which ones should be interactive with each other.
Sure. There's a whole field called AutoML, where the idea is to use machine learning to learn how to do machine learning. And so one of the classic problems in there is we've got all these different options of algorithms or methods we can use to solve a problem. Being able to look at a data set ahead of time and figure out which one the best one is a sort of a meta level learning of all this. Awesome. Maybe one more?
I think
identifying crop types using remote sensing.
Awesome. Identifying what types?
Crop types.
Crop types? Yes. So especially coming back to the idea of like aerial images and things again, can we go over a part of the country and figure out what kinds of crops are being grown? There's an article in Wired a couple weeks ago, maybe it was actually in the spring. I just had my students read it for the machine learning class, where the government of Estonia is using more machine learning methods to sort of automate things that can be done and relieve the amount of workers that need to be hired by, not necessarily the number of workers, the amount of work needed to be done. Let's do it that way. And one of the things they're doing is rather than having to send people out into fields to see whether or not hay is actually being collected by farmers, they can just look at satellite image data to see, is there hay here, yes or no? So kind of a real world, actual practical use of that right now. That was a fantastic example. One more?
To help machine learning, does the first round of machine learning choose the function space, or it does not?
So it'd be sort of this, if we think about it being at two different levels. So at one level, we'd have a bunch of different machine learning models that read in, that do the normal supervised learning thing. So we have decision trees, we've got neural networks that all read in some data and learn how to make a prediction. Above that, we've got another model that figures out which one of those is the one we should have run in the first place. So at the higher level, it's taking in general characteristics of the data and not the attributes themselves to make those kinds of predictions and stuff. So at the first level, it's the normal supervised learning. At the second level, it'd be a different feature space and that kind of thing. Does that sort of answer your question?
So the low level, researcher actually pick which model or which method we're using at the low level, and then use another machine learning to pick one of those, right?
Yes.
Okay.
Yeah.
A question from the chat. Can you explain a little bit more about what is sentiment analysis?
Great question. So sentiment analysis is, given a piece of text, be able to identify what sorts of emotions are being expressed in that, or even just is it a positive or a negative sentiment. So was the writer trying to express something positively, negatively, or a neutral statement is the general problem, but then we can separate positive and negative into different kinds of emotions as well. So another great question, and one I wish we had time to talk about later today too. Question?
I just wanted to add one more possible
Sure.
task. Having machine learning detect biases within other algorithms.
Yeah.
Oftentimes your data might reflect human biases, and you want to correct for that. You don't perpetrate or continue bias.
Yes. This is one of the big problems with machine learning right now, is that machine learning is a little bit different than human hand-coded algorithms. We had the paradigm example before, where we've got one where a person's designing an algorithm. This is what they think the set of steps should be to solve a problem. Machine learning is looking through data to find patterns for that. And so the first type, where the person is coming up with the algorithm, those tend to have, whether it's conscious or subconscious, it's natural for biases to be imposed there. Not a good thing, but human, the way we think, we automatically add those things into there. The hope with machine learning methods is that those biases can disappear. So an example of this would be facial recognition algorithms. So the best in terms of performance, initial facial recognition algorithms tended to look at shadows in a face. And so the idea was, can I see where shadows are falling to be able to identify eyes? And then from that, I know sort of what the facial outline looks like and that kind of thing. But if we're looking at shadows to be able to determine that, that works really well on white faces. It doesn't work so well with people with darker pigmentation. And so this was a bias imposed by the way a person designed the algorithm in the first place. The hope with machine learning is that these are just things looking through data. That type of decision isn't being made inside of there unless it's in the data. The problem, though, is that lots of the data we collect also have social biases and other things in them too. And so even though the algorithm doesn't have something built in it to cause that, if we're giving it data that has a bias, it's going to learn to be biased as well. And there's lots of examples of this, unfortunately, in the real world. And so one avenue of research is to actually figure out when those biases occur and try to self-correct for those. So can we look at a data set, figure out where the instances are that might cause bias, and then remove those or adapt for them and that kind of stuff. So great question, great example.
From the chat.
Sure.
Can you talk a little bit about what is / why there is controversy for causal inference using machine learning?
Sure. So this is the correlation versus causation debate, but kind of the 21st century version of it. So when we look at machine learning models, and we'll see how these methods work in a little bit when we get to neural nets and random forest and stuff. But they're really finding patterns, and sometimes that's no more than just finding causation. So they can see that these types of attribute values occur when a particular category occurs that we're trying to predict. That doesn't necessarily mean that those things caused it in the first place. So a lot of these methods are simply finding better and better correlations in a sense, and not necessarily the causations. So we need to be careful when we interpret these models, just like we are with other kinds of statistical models and stuff too. Great question. Okay. That's supervised learning. We'll do unsupervised and reinforcement real fast, and then we will take our first break. So let's look at unsupervised learning and contrast it with supervised. The idea here being the tasks we want to do are to find patterns or relationships from a data set. So we might be interested in finding categories of human behavior. So in supervised learning, we assumed we knew the categories ahead of time, and then we wanted to assign each instance to one of those. Here we don't know the categories. We're looking to see what they are in the data. Or maybe we want to find events that frequently co-occur together too. So the example before of taking a network and finding users or people or whatever's connected with a network that are most similar to each other, so like a social network who shares the same opinions and those kinds of things, that might be this kind of task. We don't know which groups to assign people to, we're just looking for the presence of groups. Performance is going to be very different because we don't have set categories we're trying to assign, so we can't measure things like accuracy or recall. So instead, we might care about how strong or unique the patterns are that we find. So if we're looking at like groups or how we can organize instances together, we might look at the variance between them. So the less variance within a group, the stronger that relationship and the more information they share with each other. Or if we're trying to find things that frequently co-occur together, and I'll give an example of that in a second, we might look at things like lift. So how much more likely is this relationship than what we would expect by random chance? So is this a meaningful relationship or is it random? Kind of like statistical tests, but a little bit different. And our experience here is just collections of data. So we have a whole bunch of instances that have attributes, but we don't have any labels for these, no categories that we want to assign. We're just looking at the raw information. So we tend to have some pre-existing data set already. And we don't have to go through the problem of coming up with the right labels for those or categories. So oftentimes when we talk about data mining versus machine learning, a lot of the things that get lumped together with data mining tend to be more on the unsupervised learning side. There is data mining that looks at things like making predictions and stuff that fall under supervised learning, but usually, at least in like the news and stuff, when people are talking about these, machine learning is more supervised, data mining is more the unsupervised side. Question?
Can you elaborate on what you mean by the absence of labels? Because is it that you don't know what an independent and what a dependent variable is, or could you just have a bunch of variables that you're looking at relationships between?
Yeah, so we don't necessarily have any dependent variables that we're trying to figure out what the right value is for each instance and stuff. Yeah, we just have a whole bunch of independent variables. We want to know what kind of relationships exist between those. That's a great way of framing it. Thank you. Yes?
Would you be trying to then, once you have these unsupervised, or at least based off the unsupervised data, trying to figure out labels for them, or?
You could use it to assign, so we could do this in a two-step process. Like if I want to be able to take a new person in a social media group and figure out which type of user they are, I might first run unsupervised learning to come up with the categories and then go through and hand label, okay, this person belongs to this category, and then use that data to train a supervised learning model. We can definitely go that way. And in fact, what happens in neural networks actually is they're doing their own form of unsupervised learning that then feeds into a supervised learning method. Yes, great question. Yes?
Categorize the task of checking that is merged correctly into the experience one, or?
Ooh. So we take two data sets, we merge them, and we want to know if the merging worked or not. Yeah. So the two data sets themselves would definitely be the experience. I don't know. That's a great question. It'd probably be more of a supervised learning. If we had a method that could sort of look at a data set and say, did it merge correctly, yes or no, that would be a supervised learning problem. So it would be able to give us that category, yes, it merged right, or no, it did not. But merging data sets would be something when we're building the experience in the first place, for sure. Great question. Yeah.
From the chat, back to the controversy and the bias.
Sure.
Is there any way we can minimize potential for this controversy, aka bias, and based on how we proceed?
Yeah.
This is like sort of techniques to combat this bias that you're talking about.
Yeah. I don't off the top of my head have a good list of references or particular methods being used, but if you send me an email about it, I'd be happy to put some of that together and I could send that out too. Be an interesting topic for another workshop and stuff too.
Yes, absolutely.
Cool. That's a fantastic question though, and I wish I had some stuff prepared for that. Okay. So again, unsupervised learning, we want to find patterns. We don't assume any categories ahead of time. Okay, so clustering, how many people have used clustering methods maybe before in more of a statistical background? Yeah, so clustering is the classic example of unsupervised learning. We've got a lot of different instances. We want to find which one of them are most similar to each other. And from that, we get groups. So the example we've been talking about. So I can have different kinds of clusters. So one way to do this would be looking at distance-based. So find a point that represents sort of the average of that thing, and then find the ones that are closest to each other. So this is going to be looking at distances, finding everything similar to that. This is spherical clustering. We can also have hierarchical, where instead we start with every individual instance, and then we try to merge them to see which ones are most similar. So here, B and C B and C have more in common than they do with anybody else, so we lump them together. The same thing with D and E, and then we just keep combining these piecewise as we go along. So this one's just going to look at distance functions, try to assign everyone to the closest middle. This one's going to combine things. Lots of different ways of doing clustering, but the key idea is, in the end, finding things that are related to each other. Question?
So these are examples of clustering observations or cases?
Yes.
When you cluster variables, like factor analysis, would that also be considered unsupervised learning?
Yes, that would as well. So that's basically taking, and yeah, this would be looking at the rows of our spreadsheet. We could also cluster based on the columns as well. Great question. Another example of this is association rule mining. Has anybody heard of this particular topic before? Okay, cool. So this is the idea of, instead of finding which attributes are most like each other, this is which values of attributes happen together. So an example of this, where this originally was developed, was for supermarkets to be able to understand purchasing patterns of customers. So we've got different shopping carts here, different people are buying different things, and from a supermarket perspective, we want to be able to understand if somebody buys product X, which ones are they also likely to buy? So if we look at these, we see that people who buy tomatoes also buy bananas, and vice versa. People that buy milk also buy bread, but people that buy bread don't necessarily buy milk. So milk co-occurs with bread, but not necessarily the other way around. So we could generalize this to any data set, so which ages and educations go together, et cetera, et cetera. Yeah, the idea is finding which things happen together. And then from here, we can see how strong those relationships are. This is where that lift stuff comes in. So we can think about what's the random likelihood that somebody buys bread, what's the random likelihood that somebody buys milk, and then we can see, is it more likely that they buy bread with milk than if they just buy bread alone? So, in the interest of time, let's just kind of think about this one individually. Maybe later on, what kinds of tasks might be for unsupervised learning. If we go back to our big list, computer goes fast enough. So of these here we had our unsupervised example we've been talking about several different times. With the automating lit review, if I wanted to be able to find, explore, so it finds one paper, looks at all the citations, and then branches out to look at other stuff. If I want to categorize those and find papers that are closely related to each other, that might be an unsupervised learning version of that problem. Yeah, and then trying to find categories of emails that we might need to reply to first, that might also be an unsupervised problem. Okay. The last kind, any questions about unsupervised before we move on? Yeah. Yeah, great question. Okay, so there is a spectrum between supervised, where we have assigned categories for every single instance that we're learning from, Unsupervised, we assume we have none of that information. Semi-supervised occurs when we're in between those two. So maybe half of our instances we know the correct category for. So there's lots of different ways of learning in there. Things we might do is we might first cluster all the instances together so that we can share the category information with everyone that gets clustered here. So let's say I take all my instances, I find that here's a group of my survey respondents. Most of them are going to respond, is the category we know for them. Then I'm going to impute that for everybody else. And then I can use that as my supervised learning training set afterwards. So it's sort of a semi-supervised is when we're trying to look in between the two extremes. Good question. Okay. Reinforcement learning. So this is the last type. This is the less commonly talked about one, but it's also the one where a lot of research is being done at the moment that could really change the way we do things in the real world. So when we're viewing reinforcement learning, we're thinking about the computer as some sort of agent that acts in a world. We've got an agent that makes its own decisions. We've got a world that it's interacting in. And the way it works is the agent perceives some information about the world, so it knows what its current situation is. It thinks about what the right thing to do in that situation is, and then it actually takes an action, changes the world. And when it changes the world, it then perceives a new situation that it's in, a new state, and it gets some sort of feedback that says, was that a good action, yes or no? And this cycle just keeps repeating over and over. Okay, so the kinds of tasks we're looking at here are trying to find the best sequence of things to do to actually accomplish some goal, while also maximizing the feedback we get from the world. We want good feedback, we want to avoid bad feedback. So when we talk about sort of building computers that can play games, that's sort of a common one we see in the news, whether it's poker or it's a video game, etc. That's an example of reinforcement learning. It sees that it's in a current situation, maybe what the board of the game looks like, and it decides what's the best thing to do. If we're trying to build computers that are smarter about how they interact with people, that's going to be a reinforcement learning problem too. So my automated assistant example from before, and maybe even the choose your own adventure story. So deciding what's the right sequence of plot hooks and settings and stuff to give to a user would be the actions that are being chosen here. And whether the user likes it or not is going to be the feedback that it gets. Autonomous cars, at some level, learn from this too. So we do some supervised learning where we say, okay, given this situation, what's the right thing to do? But ultimately, we can't give it examples about everything, and so we let them act in the world, and they get some feedback that way too. Performance here is some sort of measure of how good the set of actions the agent's been choosing is. So that's going to mostly be the cumulative feedback it gets. So every time it takes an action, again, we get a thumbs up, thumbs down, or some number. What's the sum of those over time? And also, how quickly is it accomplishing goals? You can come up with the right sequence, but it might take forever. If there's a shorter sequence of actions, we might want that one instead. So again, human-computer interaction, we don't want the computer to take forever to do something for us. It's better if it can do it in a few steps. And the difference between this one and the other two types is that we generally start with no experience and we build it up over time. So every time the agent takes an action, it gets that next situation it's in and it's the feedback it gets, and it builds up a big collection of those, and that's what it learns from. So an illustrative example of this would be, how many people check their social media posts at least once a day? Yeah, and there's lots of stuff to look at, right? So it'd be great if the computer could, and to some extent, Facebook and Twitter and others already do this kind of thing, but it'd be great if it would learn how to show us the things we're most interested in so we don't have to weed out all the other stuff. So here, the history it's learning from the situations is the sets of articles it could show to a user. The actions it takes are which articles it actually shows you or which posts it actually shows you. And the feedback you give it is, did I like this, yes or no? So in Facebook, the things you give a thumbs up to. On Twitter, the things you retweet. Other places we might give stars, etc. We're giving it some sort of feedback. It's learning on the fly what's the right thing to do. And in terms of different kinds of tasks where this might be useful, I don't think we had any on the example before, but as I mentioned, like trying to build an assistant that helps. And that doesn't have to necessarily be an assistant to you. One thing that would be really interesting is, and this is more in survey research, not necessarily all social science, but if we have like a survey or interview, if the survey could adapt its questions. So understand if the user is likely, if they're starting to commit straightlining where they're just marking answers or they're speeding through to get done as fast as possible, can it adapt which questions it's asking to sort of get the most information or maybe slow the user down so they're sticking around? Or if we're conducting interviews where a respondent is talking to an interviewer, can we have an agent that sits around and watches the health of the interview and makes suggestions of, oh, I think you should ask this question next, or I think you should say this to sort of calm the respondent down or to perk them up and those kinds of things too. So this is a lot more forward-looking than the other kinds, but I just wanted people to be aware that this type of learning exists and might be useful in the future. Question from the chat.
Sure. With reinforcement learning, do you have to factor in multiple tests before you go live with it? Seems like there's more risk inherent in this type of model since accuracy is not there initially. So, I mean, this is just, I guess, talking about, does this need more feedback than the other types that you're talking about?
Yeah, so ultimately what would happen is you would pilot this for a while. So we'd build a system, we would test it internally or do small-scale studies with it first, and then once we know that it's working okay, then move it into production. But yeah, there's a lot of risk because if it's at the beginning, it's sort of randomly choosing the right things to do, and if we put that into real world, we could just get chaos. So yes, fantastic question. Okay. Any others about reinforcement learning? Okay, so to recap, machine learning, we can view it as a problem-solving paradigm, where it's a way of thinking about solving problems. We think about having tasks we want to accomplish. Different kinds of tasks lead to different kinds of learning. If the task is to assign a category or make a prediction, that's supervised learning. If it's trying to find relationships, it's unsupervised learning. And if we want to just figure out how to act from the get-go, then that's going to be reinforcement learning. And then we have different ways of measuring performance and expertise, or experience, I mean. And that's the general umbrella of machine learning. Let's go ahead and take our first break. Let's take a 10-minute or so, and then we'll come back together and we'll walk through how we actually do this stuff. So we're going to focus for the rest of the day on supervised learning, because that's what most people talk about, and we'll walk through an example in code and some other stuff. So. Thanks.